Right now, more than 10 NASA spacecraft are tracking an interstellar comet that refuses to die. 3I Atlas has survived its closest approach to the Sun and absorbed multiple direct impacts from solar plasma ejections, conditions that just days ago shattered 3 ordinary comets into fragments. This should not be happening. Theory predicts that objects traveling from beyond our solar system, forged in different stellar nurseries under unknown conditions, should be fragile, volatile, prone to disintegration when exposed to our Sun's radiation and gravitational stress. 3I Atlas is doing the opposite. It endures. Scientists are unsettled not because the comet broke apart, but because it has not. The confusion began with a rumor. Social media channels devoted to amateur astronomy lit up with claims that 3I Atlas had fragmented, scattering debris across its trajectory. The Solar Astronomy Laboratory of the Space Research Institute in Moscow and the Institute of Solar Terrestrial Physics moved quickly to clarify that the interstellar visitor remains intact. The breakup visible in recent images belongs to a different object entirely. Comet C2025K1 Atlas, a conventional solar system resident with a superficially similar designation. Observations from November 12th and 13th captured C2025K1's nucleus splitting into at least 3 major fragments, with smaller pieces detectable at higher resolution. The misidentification was understandable. Both comets share part of the same name. Both were under intense scrutiny, but only one of them is still whole. Here is where it gets interesting. C2025K1 is not an isolated casualty. In the span of weeks, comet C2025 R2 Swan disintegrated. Then C2025V1, discovered by Gennady Borisov, the same amateur astronomer who identified the second ever confirmed interstellar object, 2E Borisov, back in 2019, also broke apart. 3 comets, 3 destructions, all within a compressed time frame. The Sun has been unusually active. Solar plasma bursts, coronal mass ejections, hurling billions of tons of charged particles outward at speeds exceeding 1,000,000 miles per hour, have been hammering objects in near-solar space. For delicate assemblages of ice, dust, and loosely bound rock, comets, in other words, this environment is lethal. Nuclei held together by little more than frozen volatiles and weak gravitational self-attraction simply cannot withstand the thermal shock and electromagnetic bombardment. They crack, they crumble, they vanish into expanding clouds of vapor and grit. 3I Atlas has taken those same hits and remained coherent. Stop and consider that. This is an object that originated light years away, in a region of space with entirely different chemistry, different temperatures, different radiation fields during its formation. Interstellar objects spend millions or billions of years drifting through the near vacuum between stars, exposed to cosmic rays and the faint background glow of the galaxy. When they enter our solar system, the sudden heat and gravitational perturbation from our Sun represents a violent environmental shift. The expectation, grounded in decades of cometary science, is that interstellar visitors should be more fragile than native comets, not less. Their ices might sublimate at different rates. Their internal structures might lack the binding strength forged under our Sun's specific influence during the solar system's formation. Yet here stands 3I Atlas, absorbing punishment that shattered its neighbors and continuing on its trajectory without apparent degradation. Avi Loeb has taken notice. The Israeli-American theoretical physicist who directs the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics has built a controversial reputation over recent years for advocating the possibility, however remote, that certain anomalous astronomical objects might have artificial origins. His focus previously centered on 1I Oumuamua, the first recognized interstellar visitor, which exhibited non-gravitational acceleration that some attributed to outgassing, but which left room for alternate explanations. Loeb proposed, amid substantial skepticism from the broader scientific community, that Oumuamua could represent a light sail or probe from an extraterrestrial civilization. The hypothesis generated more headlines than peer support, but it forced a conversation about how science distinguishes natural from artificial when dealing with objects whose origins lie beyond direct observation. Now Loeb is pointing to 3I Atlas. Specifically, he is citing its exceptional durability as evidence consistent with an artificial structure. The argument runs as follows. Natural comets, composed of primordial ice and dust aggregated loosely over eons, fracture under stress. An engineered object built with intentional structural integrity, perhaps a metal-rich framework or composite materials designed to endure interstellar travel, would resist fragmentation. The fact that 3I Atlas has survived conditions lethal to ordinary comets does not prove artificiality, but it opens a door that most scientists would prefer to keep closed. It introduces a data point difficult to reconcile with the standard model of what interstellar comets should be. Here is the problem. Durability alone cannot distinguish between an unusually robust natural object and an artificial one. Comets vary widely in composition. Some contain higher fractions of refractory materials, silicates, metal grains, that provide structural strength. Some have undergone previous close passes to other stars, which could have baked their outer layers into a hardened crust capable of shielding the interior. Some might have formed in environments richer in carbon compounds that polymerize under radiation into tough organic tars. The universe is full of edge cases. 3I Atlas could simply represent the far end of the natural distribution, an object whose formation conditions happen to produce something more resilient than the average comet. To leap from this is unusually strong. To this might be artificial, requires not just one anomaly, but a cluster of them, multiple independent lines of evidence that collectively resist conventional explanation. Read between the lines of the institutional responses. When the Solar Astronomy Laboratory and the Institute of Solar Terrestrial Physics issued their clarification, they did not merely correct a case of mistaken identity. They also posed a question. Is fragmentation of 3I Atlas even possible? The phrasing is careful. It does not assert impossibility. It does not speculate on artificial construction. It simply invites examination of the physical scenario. Could this object break apart under any plausible set of conditions it might encounter in our solar system? If not, why not? If so, what would it take? The framing suggests that scientists directly involved in monitoring the comet recognize something unusual is occurring, even if they are not yet prepared to attach extraordinary interpretations to it. The Sun, indifferent to human speculation, continues its assault. A powerful solar flare erupted on October 17th, releasing a surge of electromagnetic radiation across the spectrum and launching a coronal mass ejection into space. These plasma clouds do not travel instantaneously. They propagate outward at speeds typically ranging from 250 to 3,000 kilometers per second, depending on the energy of the eruption. Given the timing, from October 17th to the present moment, the leading edge of that plasma outburst is expected to intersect the trajectory of 3I Atlas within hours. This is not a glancing encounter, it is a direct hit. The comet will be engulfed in a maelstrom of charged particles, magnetic fields, and shock waves that have already demonstrated their capacity to tear apart cometary nuclei. 3 comets have fallen. 3I Atlas is about to face another test. Here is where things get strange. NASA has responded to this situation not with routine observation, but with the launch of a unique, coordinated campaign involving more than 10 spacecraft. This is an extraordinary allocation of resources. Space-based observatories operate on tightly scheduled timelines with observation windows allocated months or years in advance. To redirect more than 10 spacecraft, instruments aboard solar monitoring satellites, space telescopes, planetary probes toward a single transient target suggests that mission planners recognize an opportunity that justifies disrupting existing schedules. What kind of opportunity? Most obviously, the chance to observe an interstellar object under extreme conditions with unprecedented instrumental coverage. But the scale of the response also signals that scientists expect to see something worth the effort, something that cannot be captured through ground-based telescopes or a single satellite. Now about the data. Understanding what makes 3I Atlas unusual requires understanding what normal cometary behavior looks like. A typical comet nucleus measures anywhere from a few hundred meters to tens of kilometers across. It is not a solid chunk of rock, but rather a dirty snowball, a heterogeneous mixture of water ice, frozen carbon dioxide, frozen methane, and dust particles, all loosely aggregated. As a comet approaches the sun, solar radiation heats the surface. Ices sublimate directly from solid to gas without passing through a liquid phase. This outgassing creates the visible coma, a cloud of gas and dust surrounding the nucleus, and the tail, which streams away from the sun under the pressure of solar radiation and the solar wind. The process is inherently violent at the molecular level. Gas erupts from fissures and vents. Differential heating causes thermal stress. If the nucleus has pre-existing cracks or weak zones, the outgassing can blow chunks apart. Add the mechanical shock of a coronal mass ejection, sudden compression, electromagnetic forces acting on ionized material, and fragmentation becomes almost inevitable for structurally weak objects. See 2025 K1 Atlas, fragmented between November 12th and 13th. Observations recorded the nucleus splitting into at least 3 large fragments. The term large is relative. In cometary terms, it likely means pieces ranging from hundreds of meters to perhaps a kilometer or more in diameter. Higher resolution imaging revealed smaller debris as well, suggesting a cascade of breakup events. This is textbook disintegration. The parent nucleus, unable to withstand internal pressure from outgassing or external stress from solar activity, simply came apart. Each fragment then became its own miniature comet, surrounded by its own small coma as ices on the freshly exposed surfaces sublimated. Over time, these fragments will continue to break down, eventually dispersing into a debris stream that might produce a meteor shower if Earth's orbit happens to cross it centuries from now. C-2025, R2 Swan, and C-2025V1 followed similar patterns. Swan, monitored by the Solar and Heliospheric Observatory, showed clear signs of nuclear fragmentation, consistent with thermal and mechanical stress. C-2025V1, discovered by Gennady Borisov, added a layer of irony to the situation. Borisov, who became internationally known for detecting 2I Borisov, the second confirmed interstellar object, had now found an ordinary comet that behaved exactly as theory predicts. It fell apart. The interstellar object he discovered previously showed no such fragility. Neither does 3I Atlas. The pattern emerging here is not that interstellar objects are uniformly strange, but that 3I Atlas specifically is resisting a fate that even robust solar system comets cannot escape under current solar conditions. Think about what that means for its internal structure. If 3I Atlas were a loose aggregate, like a rubble pile held together by microgravity and frozen volatiles, the thermal shock alone would cause it to fracture. If it were predominantly ice with minimal rocky content, outgassing would erode it rapidly, potentially spinning fragments off as jets of gas exerted torque on the nucleus. If it had a high porosity, lots of internal voids and weak zones, the pressure from sublimating ices would find those weaknesses and exploit them, cracking the object open from the inside. For 3I Atlas to remain intact, it must possess either a composition or a structure, or both, that differs fundamentally from the norm. Possibilities include a much higher fraction of refractory material, giving it the strength of a rock rather than a snowball. It might have a dense, non-porous interior that limits the pathways for gas to escape, preventing the buildup of internal pressure. It could be sheathed in a thick, radiation-hardened crust formed during its long journey through interstellar space, a protective shell that insulates the interior from rapid heating. Or, as Loeb would argue, it could be something else entirely, an artificial object designed to survive interstellar transit would need to endure micrometeorite impacts, cosmic radiation, and the thermal extremes of passing near stars. Such an object would likely incorporate materials far stronger than water ice, metals, ceramics, carbon composites. It would be engineered to dissipate heat, to maintain structural integrity under stress, to function across a wide range of environments. If a civilization capable of interstellar travel sent probes into the galaxy, those probes would not be fragile. They would be built to last. The durability of 3I Atlas is consistent with that profile, even if it does not require it. The scientific community remains divided, though divided may be too strong a word. The majority of astronomers favor natural explanations, pointing to the vast range of cometary compositions and the fact that every previous anomaly attributed to interstellar objects, such as Oumuamua's acceleration, eventually found plausible natural mechanisms, even if the data were insufficient to confirm them definitively. A smaller, vocal minority, including Loeb, argue that science should not dismiss artificial explanations a priori simply because they seem improbable. The debate is less about what 3I Atlas is, and more about what standards of evidence should apply when considering hypotheses that carry profound implications. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury in New Zealand who has studied trans-Neptunian objects and cometary populations, offered a measured perspective in a recent interview. Interstellar objects are, by definition, outliers. They formed in other star systems under conditions we can only infer. We should expect them to surprise us. The question is whether the surprise is due to chemistry and physics we have not fully explored, or whether it requires us to invoke something beyond natural processes. Right now, the data on 3I Atlas are intriguing, but they are not yet in the realm of the inexplicable. Her phrasing, "not yet," leaves the door open. It acknowledges that as observations continue, the object might reveal characteristics that exhaust natural explanations. But it also emphasizes patience, the scientific method's insistence on ruling out the mundane before embracing the extraordinary. Dr. Matthew Knight, a comet researcher at the U.S. Naval Research Laboratory, focuses on the observational challenges. We are looking at an object millions of kilometers away, resolving details on the scale of meters or tens of meters if we are lucky. We see the coma, the tail, the overall brightness, but we do not have direct imaging of the nucleus surface. We do not have spectra at sufficient resolution to definitively characterize the composition. We are making inferences from indirect evidence. That is not a criticism of the science. It is the reality of studying these objects. But it means we need to be cautious about building elaborate models on limited data. Knight's caution is procedural, not dismissive. He is pointing out that the absence of fragmentation is a single data point, and single data points rarely overturn established theories. Yet the absence of fragmentation is not occurring in isolation. The multi-spacecraft observation campaign NASA has organized will produce a wealth of data. Spectroscopic measurements revealing the chemical composition of the coma. Photometric data tracking brightness variations that could indicate surface features or rotation. Polarimetry that might shed light on the size and properties of dust grains. Ultraviolet observations capturing the behavior of outgassing. If 3I Atlas is merely an unusually tough natural comet, these data should show signatures consistent with known cometary materials: water vapor, carbon monoxide, carbon dioxide, dust grains composed of silicates and organics. If the data instead reveal anomalies, unexpected spectral lines, unusual dust properties, brightness variations that do not match rotational models, the mystery will deepen. And, by the way, I would love to hear from you right now. Drop a comment and let me know where you are watching from and what you think will happen as this comet continues its journey through our solar system. Do you think it will finally break apart? Or will it keep defying all expectations? What do you make of the artificial origin theory? If you are finding this fascinating, hit that like button and subscribe to the channel so you do not miss any updates as this incredible story unfolds. Now let us continue. The spacecraft involved in the campaign span a range of capabilities. The Solar and Heliospheric Observatory, orbiting the Sun-Earth L1 Lagrange point, provides continuous solar monitoring and has instruments capable of tracking comets in the inner solar system. The Solar Dynamics Observatory, also focused on solar phenomena, can capture high-resolution images of the Sun's corona and any objects transiting near it. The Parker Solar Probe, designed to fly closer to the Sun than any previous mission, might offer unique perspectives if 3I Atlas passes within its observational range. The Hubble Space Telescope, though aging, remains one of the most powerful optical instruments available, capable of resolving fine details in the comet's coma and tail. The James Webb Space Telescope, with its infrared sensitivity, can detect heat signatures and molecular emissions invisible to optical telescopes, potentially revealing the temperature and composition of the nucleus itself. Ground-based observatories are also contributing, though atmospheric distortion limits their resolution compared to space-based platforms. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, and numerous smaller facilities are tracking 3I Atlas, gathering data on its trajectory, spectral characteristics, and any changes in activity. Amateur astronomers, using equipment that would have been professional grade a generation ago, are adding their observations to the collective dataset. This is not a single mission, but a coordinated global effort, a convergence of resources driven by the recognition that opportunities to study interstellar objects are rare and fleeting. Consider the logistics. 3I Atlas was detected earlier this year, likely by the Asteroid Terrestrial Impact Last Alert System, ATLAS, hence the designation. Determining that an object is interstellar requires precise measurements of its orbit. Comets and asteroids native to the solar system follow elliptical or parabolic paths bound to the Sun's gravity. Interstellar objects follow hyperbolic trajectories, entering the solar system from the direction of a specific point in the sky, swinging around the Sun, and then departing in a different direction, never to return. Calculating these orbits demands multiple observations spread over weeks or months, combined with sophisticated models accounting for gravitational perturbations from the planets and non-gravitational forces like outgassing. By the time scientists confirmed 3I Atlas was interstellar, it was already well into its encounter with the inner solar system, limiting the window for detailed study. The decision to deploy more than 10 spacecraft on short notice reflects an understanding that this window will not last. Within months, 3I Atlas will recede beyond the effective range of most instruments, becoming just another faint dot, indistinguishable from background stars. The plasma outburst expected to strike today adds urgency. If the impact causes fragmentation, the observation campaign will document the breakup in unprecedented detail, providing insights into the comet's structural properties and the mechanics of plasma-induced disintegration. If the impact does not cause fragmentation, if 3I Atlas absorbs the blow and continues intact, the case for anomalous durability strengthens considerably. Either outcome is scientifically valuable, but only one of them will fuel ongoing controversy. Loeb is not alone in his willingness to consider unconventional explanations, though he is among the most prominent. The Galileo Project, an initiative he founded, aims to search for potential evidence of extraterrestrial technological artifacts using systematic observational methods. The project's stated goal is to bring the question of alien technology into the domain of empirical science, rather than leaving it to speculation or stigma. Critics argue that the prior probability of encountering an artificial object is so low that extraordinary evidence is required, and that interpreting ambiguous data as artificial when natural explanations remain viable is premature. Supporters counter that science advances by investigating anomalies and that dismissing possibilities without investigation is itself unscientific. The broader context includes the unidentified aerial phenomena investigations conducted by the U.S. government, which have shifted the conversation around unexplained observations from fringe territory to legitimate inquiry. While UAP reports largely concern atmospheric phenomena and potential advanced human-made technology, they have created a cultural and institutional environment slightly more receptive to considering non-standard hypotheses. This does not validate any specific claim about 3I Atlas, but it does mean that when a scientist like Loeb proposes artificial origins for an anomalous object, the response is no longer immediate ridicule, but rather a mix of skepticism, interest, and demands for rigorous evidence. What would constitute rigorous evidence? Spectroscopy detecting synthetic compounds or isotopic ratios inconsistent with natural nucleosynthesis. Geometric structures visible in high-resolution imaging, edges, symmetries, repeating patterns that resist geological explanation, radio emissions or other signals that imply intentional transmission, trajectory adjustments that cannot be explained by outgassing or gravitational interactions. A single anomaly, however striking, is insufficient. Nature is too diverse, too full of edge cases. But multiple independent anomalies, each difficult to explain naturally, begin to form a pattern that demands consideration of alternatives. So far, 3I Atlas has provided one clear anomaly: its durability. The spectroscopic data currently available show emission lines consistent with cometary outgassing, water, carbon monoxide, dust. The trajectory follows a hyperbolic orbit consistent with an interstellar origin, but without unexplained accelerations. The brightness variations appear consistent with a rotating, irregularly shaped nucleus, though the details are still being analyzed. None of these findings, in isolation, suggest artificiality. The durability stands alone, for now, as the unexplained feature. Whether it remains alone or whether the ongoing observation campaign uncovers additional anomalies will determine the direction of the scientific conversation. The historical precedent is not encouraging for those hoping for exotic explanations. When Oumuamua was first detected in 2017, its elongated shape, inferred from brightness variations, sparked immediate speculation. No known asteroid or comet had such an extreme aspect ratio. As data accumulated, the object exhibited non-gravitational acceleration, moving away from the Sun slightly faster than gravity alone would predict. Outgassing was the obvious explanation. Comets routinely accelerate due to the rocket effect of sublimating ices. But Oumuamua showed no visible coma, no tail, no spectroscopic evidence of outgassing. It appeared inert, yet it was accelerating. Loeb proposed that solar radiation pressure acting on a thin, flat object, a light sail, could produce the observed acceleration without requiring outgassing. The hypothesis generated intense debate. Subsequent studies suggested alternatives. Perhaps Oumuamua was composed primarily of nitrogen ice, which would sublimate without producing detectable emissions. Perhaps its spin state and shape amplified radiation pressure effects. Perhaps it had a thick crust that masked outgassing activity. None of these explanations were definitive, but they were plausible enough to prevent the artificial hypothesis from gaining traction. 3I Atlas is different in one key respect. It is still here, still observable, still under scrutiny. Oumuamua passed through the inner solar system and vanished before most of the world's telescopes could be trained on it. The data were sparse, the observation window narrow. 3I Atlas, by contrast, is the subject of a coordinated international campaign with instruments far more advanced than those casually available in 2017. If anomalies exist, they will be found. If the object is natural, the data will confirm it. The ambiguity that plagued Oumuamua should not plague 3I Atlas. Unless, of course, the object is designed to be ambiguous. This is where the speculation becomes recursive and ultimately unproductive without new data. If an extraterrestrial civilization wanted to send a probe that could observe star systems without revealing its artificial nature, it might design that probe to mimic natural objects, comets, asteroids, while incorporating features that allow it to survive conditions natural objects cannot. Such a probe would be durable, but not implausibly so. It would exhibit outgassing to maintain the appearance of a comet, but perhaps with carefully controlled composition. It would follow a trajectory that appears natural, while subtly adjusting course in ways that blend into observational uncertainties. Distinguishing such an object from a genuinely unusual natural one would be extraordinarily difficult without close-up investigation, the kind of investigation that requires sending a spacecraft to rendezvous with it, a mission that would take years to plan and execute, by which time 3I Atlas will be long gone. This is the frustration inherent in studying interstellar visitors. They appear without warning, offer a brief window of observability, and then depart, never to return. The solar system is vast, and the intervals between interstellar visitors are measured in years or decades. 1I Oumuamua in 2017, 2I Borisov in 2019, now 3I Atlas in 2025, 3 objects in 8 years. Each one a unique opportunity, each one gone before comprehensive study is possible. The dream of planetary scientists is to detect an interstellar object early enough while it is still beyond the orbit of Jupiter or Saturn that a mission could be launched to intercept it. The European Space Agency has proposed Comet Interceptor, a spacecraft designed to wait in space until a suitable target is identified, then rapidly redirect to rendezvous with it. Launch is planned for the late 2020s. If successful, it will be the first mission capable of close-up investigation of a long-period comet or interstellar object. But 3I Atlas will be gone by then. The question of why interstellar objects appear so rarely is itself a subject of debate. The galaxy contains hundreds of billions of stars. Planetary formation is common, and the processes that eject comets and asteroids from star systems are well understood. Gravitational interactions with giant planets can fling small bodies into interstellar space at velocities exceeding the escape speed of the star. Over billions of years, the galaxy should be filled with a vast population of rogue comets, asteroids, and planetary fragments wandering between the stars. Statistical models predict that the solar system should be visited by several interstellar objects per year, most of them too small or too faint to detect. The fact that only 3 have been confirmed suggests either that the models overestimate the population, or that detection capabilities are still insufficient, or that interstellar objects differ from solar system objects in ways that make them harder to spot. Perhaps they are darker, less active, or smaller than expected. If Loeb is correct, and some fraction of interstellar objects are artificial, the rarity makes a different kind of sense. Probes would be launched intentionally, targeted toward stars of interest rather than randomly ejected. Their numbers would depend on the density of technological civilizations and their propensity for exploration, factors about which humanity has no data. The famous Drake equation attempts to estimate the number of communicating civilizations in the galaxy by multiplying probabilities related to star formation, planet formation, the emergence of life, the development of intelligence, and the longevity of technological societies. Even optimistic estimates yield numbers that could mean the nearest civilization is hundreds or thousands of light years away. If probes are rare, it is because their makers are rare. If 3I Atlas is such a probe, its arrival is not a routine event, but an encounter with profound implications. Here is where the uncertainty becomes almost unbearable. The data exist, or will exist, within days. NASA's multi-spacecraft campaign is underway. Observations are being recorded, analyzed, cross-checked. Somewhere in that data might be a signal that shifts the entire conversation, an isotopic anomaly, a structural feature, a behavior that defies natural explanation. Or the data might confirm, with increasing confidence, that 3I Atlas is simply a very tough comet, the product of formation conditions slightly outside the norm, but entirely within the bounds of known physics and chemistry. Scientists involved in the campaign are not talking publicly about preliminary findings, a standard precaution to avoid disseminating results before peer review. The silence is both prudent and maddening. Loeb, to his credit, has been explicit about the standards he would apply. In interviews and published essays, he has stated that extraordinary claims require extraordinary evidence, but that evidence can only be gathered if the hypothesis is taken seriously enough to motivate the observations. He distinguishes between advocating for an explanation and advocating for the investigation of an explanation. The former is premature without data. The latter is simply good science. Whether his colleagues agree with this framing is another matter. Some view his public statements as harmful, fearing that they encourage sensationalism and undermine public trust in scientific rigor. Others see him as performing a valuable service, pushing the boundaries of acceptable inquiry and ensuring that unconventional ideas are not dismissed solely due to conformity pressure. The physics of coronal mass ejections provides another lens through which to examine 3I Atlas's durability. When a CME strikes a comet, the interaction is complex. The leading edge of the plasma cloud is a shock wave, a region where the density, temperature, and magnetic field strength increase abruptly. Behind the shock, the plasma itself, protons, electrons, heavier ions, streams past the comet at hundreds of kilometers per second. If the comet has an active coma, the solar wind interacts with the outgassing, compressing the coma on the sunward side and stretching the tail in the anti-sunward direction. The magnetic fields embedded in the plasma can induce currents in any conductive material within the comet, heating it through resistive dissipation. The charged particles can sputter atoms off the surface, eroding the nucleus directly. The cumulative effect is a sudden, intense pulse of energy deposition and mechanical stress. For C2025K1, C2025R2 Swan, and C2025V1, this was lethal. The nuclei, already weakened by outgassing and thermal stress from solar heating, could not absorb the additional energy without fracturing. For 3I Atlas, the previous CME impacts, plural because the Sun has been active and multiple ejections have occurred, left the object intact. The upcoming impact from the October 17th flare will provide another test, one that is likely to be the most violent yet, given the power of the originating flare. If 3I Atlas survives, the case for anomalous strength will become very difficult to dismiss with standard cometary models. Think about what that means for material science. The strongest natural materials in comets are silicate grains and metal inclusions, remnants of the dust and gas cloud from which the comet's parent star system formed. These materials can have compressive strengths on the order of hundreds of megapascals, comparable to concrete or weak rock. Ices, by contrast, have strengths measured in kilopascals, thousands of times weaker. A comet that is mostly ice with some rocky inclusions will have an overall strength dominated by the ice, making it fragile. A comet with a much higher rock-to-ice ratio would be stronger, but it would also be less active, producing less outgassing and a fainter coma. 3I Atlas is active. It has a visible coma and tail, yet it is strong. Reconciling these properties requires either a composition that is both volatile-rich and structurally robust, or a configuration where a strong outer shell protects a more typical interior. The radiation-hardened crust hypothesis is appealing because it explains both durability and activity. Cosmic rays and ultraviolet light can break chemical bonds in organic molecules, causing them to cross-link into complex polymers. Over millions of years in interstellar space, the surface of an icy body would accumulate a layer of these refractory organics, forming a dark, tough crust. When the object enters a star system and begins to warm, the crust acts as insulation, slowing the sublimation of interior ices. But cracks in the crust, or thin spots, allow gas to escape, producing the observed activity. The crust itself resists fragmentation, holding the nucleus together even under stress. This mechanism is entirely natural, requires no exotic materials, and is consistent with the behavior of some long-period comets in our own solar system that have survived multiple close passes to the Sun. Testing the crust hypothesis requires spectroscopy capable of identifying the specific organic molecules present in the coma. If the outgassing includes complex hydrocarbons or nitrogen-bearing compounds formed by radiation processing, it would support the idea of a radiation-hardened surface. If the spectroscopy instead shows simple molecules like water, carbon monoxide, and carbon dioxide, with little evidence of complex organics, the crust hypothesis becomes less convincing. The James Webb Space Telescope's infrared instruments are ideally suited for this kind of analysis. JWST can detect faint emission lines from molecules that are invisible to optical telescopes, building a detailed chemical inventory of the coma. If the data from JWST are included in the multi-spacecraft campaign, they should provide clarity. The trajectory analysis offers another angle. Interstellar objects enter the solar system with velocities determined by their motion relative to the local standard of rest. the average velocity of stars in the Sun's neighborhood of the galaxy. Typical encounter velocities are on the order of 20 to 30 kilometers per second, though this can vary. As the object approaches the Sun, it accelerates due to gravity, reaching peak velocity at perihelion, the closest point to the Sun, then decelerates as it climbs back out of the Sun's gravity well. Non-gravitational forces, if present, modify this trajectory. Outgassing exerts a force in the direction opposite the gas flow. If the outgassing is asymmetric due to the object's rotation or surface features, the force can have components that change the orbit's shape, orientation, or energy. Precisely measuring these changes requires tracking the object's position over weeks or months and fitting the data to models that account for all known forces. For 3I Atlas, the preliminary trajectory data indicated a hyperbolic orbit consistent with an interstellar origin, but detailed analyses of non-gravitational perturbations have not yet been published. If such perturbations exist and can be fully explained by outgassing models, it would argue against artificial propulsion. If the perturbations are anomalous, too large, too small, or in the wrong direction, it would raise questions. Oumuamua's acceleration was anomalous in the sense that it occurred without visible outgassing, but subsequent models demonstrated that even a small amount of outgassing below detection thresholds could produce the observed effect. The lesson is that absence of evidence is not evidence of absence, and that orbital anomalies alone are rarely conclusive. Gennady Borisov's role highlights the human side of interstellar object discovery. His 2I Borisov behaved like a normal comet, suggesting such visitors need not be exotic. In contrast, 3I Atlas's unexplained resilience is what makes it unsettling. Recent events form a compressed timeline. A major solar flare on October 17th, later plasma impacts on 3I Atlas, the fragmentation of several ordinary comets, including C2025K1, and widespread rumor-driven confusion. Scientists clarified that 3I Atlas remains intact, prompting theories ranging from anomalous natural strength to artificial construction. The comet is rapidly departing the solar system, making the current observations the only ones humanity is likely to obtain. Future surveys, such as the Vera C. Rubin Observatory, will detect many more interstellar objects, revealing whether 3I Atlas is an outlier or part of a broader pattern. Its behavior also touches on deeper questions: panspermia, technosignatures, and the possibility of artificial probes. Yet the evidence so far is limited to a single anomaly: the absence of fragmentation under extreme stress. Instruments now monitor its response to an incoming coronal mass ejection, a crucial test that could either resolve the mystery with a natural explanation or intensify it. Whether 3I Atlas breaks apart or continues to defy expectations, the results will shape our understanding of interstellar visitors and perhaps